Would they come through anyway?
Huh?
Would they come through anyway?
Oh, it's like a scene that is just a QR code.
Yeah, but wouldn't that be in the starting point later?
No, I just need to leave it up for a second.
Oh, okay. You're all set? Hello everyone, thank you for coming. This is not our final talk for the semester, but final talk for this executive team with John, and he's going to go part of
Thanks, Jay. Well, welcome everybody. Thanks for coming along. So thanks to Quinn and Jay and the Mars team for the invitation. You're the Mechatronics and Robotics Society, right? I'm about to talk to you about digital design and software and operating systems. But I'm going to try and present at a level that even if you haven't done any of this stuff, you'll at least get the gist of what I'm talking about. So what I'm going to talk about today is something called Reconfigurable System on Chip. I had a sort of 15-year career, I guess, in this space, both academic and industry, and I'll talk a little bit about some of that today. So here is, well, I'll get to that in a moment. First of all, I would like to acknowledge the Yagara and Turrbal people, traditional custodians of this land, St. Lucia, and more broadly, Meanjin and Brisbane, and acknowledge their contributions to Australian society and their leaders, both past, present, and emerging. And also, in case you've been living under a rock for the last 6 months, we have a referendum on Saturday to vote on a pretty small change to Australia's constitution to just enshrine an advisory body into the constitution that can make representations to Parliament. That's the end of the story. So if you do nothing else in regards to that, I encourage you to actually just do a little bit of research, Google it. Has anyone seen that Briggs video? It's like, yeah, right, it's gold. Anyway, so yeah, this is Aboriginal land and we don't have a treaty. We moved in and we're still here. So this is kind of broadly what I'm going to talk about. I cobbled this deck together today from, there's a bit of new stuff in here. Excuse me, a lot of it is actually just bits and pieces that I've pulled out from presentations I've given in the past. So I'm doing an FPGAs 101. What's an FPGA? And you need to understand this. This bit of the talk, my little, I think possibly my career claim to fame, I gave a talk that had some of this stuff in it at LinuxConf AU about 10 years ago. And Vint Cerf was in the audience. Anyone knows who Vint Cerf is, right? He's pretty much one of the founders of the modern internet and general kind of internet guru. So that was a bit nerve-wracking. He came up after me, after I spoke, and he said, now I understand what FPGAs are. Thank you very much. So I taught Vint Cerf what an FPGA is. So hopefully I'll teach you too. He's a very smart guy, but so are you folks. I'm going to have a little bit of a conversation about CPUs, everyone knows what a CPU is, versus FPGAs, what they're good at, what they're bad at. And this sets us up nicely for the core of the technical discussion tonight, which is reconfigurable systems on chip. I could lecture an entire semester on this stuff, right? So I'm going to be pretty shallow today. Really, my goal is just to give you a taste for the technology, perhaps an interest, and if that sticks, maybe inspire you to either do a bit of study here at UQ. We do teach some of this stuff, not as much as back in the day. I'll come to a bit of history there. And yeah, I'm going to give a quick history up to sort of current generation devices, and then maybe a few final words just to kind of motivate you and help you understand where this stuff fits in the Australian electronics industry, because that's, and globally, but in particular the Australian electronics industry. So that's what I want to do today. I'm happy to take questions. Those of you who know me from CSSC 2310, you know, my apologies, but also you know how easily distracted I am by good questions, so we'll just see how we go, and I'm going to aim to finish at about 7. Yeah, so let's get into it. So just a tiny little bit more about me. So as I said, you know me from such hits as CSSC 2310. I have undergraduate computer science and electronic engineering degrees. I did a double degree up the river at QUT back in the 90s. I did a PhD in 3D computer vision and sensing, which was pretty cool stuff. My PhD is now kind of a library call. That's just the nature of research, but it's a while ago now. And actually, I'm left out of line there, but I basically created a job for myself at the early kind of reconfigurable computing group at QUT. So we were part of a thing called FedSat. It was a cooperative research centre to design and build a satellite in Australia with a bunch of science payloads on it and launch it. And I got involved. One of the experiments on that was one of the first reconfigurable logic devices, FPGAs, to ever be flown in space, right? And so there was a payload that was, co-designed with Johns Hopkins. Anyway, I talked myself into a job there, and that was my first exposure to the concepts I'm talking about today, right? So there's a quick little lesson there, which is it's never too late to learn new stuff, right? So I built a career out of this and a business. And the other lesson is I don't think I've ever applied for a job out of the newspaper in my life, right? So if you do the things like you're doing here, showing up, being interested, being engaged, hassling supervisors for thesis projects nice and early, all that kind of stuff, right? That is how you make your career, right? So anyway, in 2002, Professor Neil Bergman, he left QUT and he came to start up a new lab here. That was a reconfigurable computing group. And I just hassled him until he had enough research funds to give me a job. And I came here to UQ. So that's a long time ago. That's 20 years ago. I had a lot more hair then and fewer children. So then I was here for about 4 or 5 years, and the work that I did here with Neil, and I'll talk a little bit more about this in a minute, got spun out into a company called Petalogics, which I ran and then eventually sold about 6 or 7 years later to Xilinx, who are now AMD. So a little bit about that later. I should disclose, by the way, my technical experience with this stuff is a little bit dated, right? So I kind of left the reconfigurable computing space, roughly 10 years ago. I sort of dabbled a little bit consulting and training and all that sort of stuff. Came back to UQ. These days I do cybersecurity and I teach 2310. However, I have a consulting business on the side doing cybersecurity for embedded systems, and my first 2 clients are both using the technologies that I'm talking about here today, right? So it's another kind of evidence point, I guess, for the relevance of this stuff in the Australian electronics industry, and potentially, if you're interested, to you and your careers. Anyway, let's get into it. Who knows? Who's heard of FPGAs? Anybody? Yeah, most people. Okay. Has anyone ever used one? Anyone ever done anything with it? Yeah, couple. Okay, nice. So FPGA stands for Field-programmable Gate Array, and the field in this sense means like in the field. It can be programmed in the field. So you probably have at least a basic understanding of semiconductor manufacture, right? So we dope silicon and we produce multiple mask layers, and we deposit doped silicon and metal layers, and we build up transistors on a wafer, and then we slice them up, we package them, we attach them to pins. The thing about those is that obviously once they're manufactured, the device just does what it does, right? So my phone's probably got a Qualcomm CPU of some kind in it. It's always going to be a Qualcomm CPU, a really fast one, a really powerful one, but that's what it does. So FPGAs are different. They are general purpose programmable digital logic devices, meaning that the digital function that they implement, and we'll talk in a minute about the basic building blocks, the digital function that they implement is software programmable. So when you turn these things on, they're kind of just sitting there. There's all this latent kind of capacity and capability and potential, but they don't actually do anything. And it's only through the process of configuring these devices through a sort of an SRAM-based programming process that they take on their digital identity. So this is, I've stolen every figure from this thing. This one's from Wikipedia. The Wikipedia page on FPGAs is not a bad place to start, actually. So this is the sort of the simplified fundamental logic cell in an FPGA. So if you've ever done any electronics, you might recognize some things here. So we've got 4 inputs on the side. They're single bit inputs, right? We've got some lookup tables. So those inputs can be presented, and the contents of those lookup tables are programmable at power on, right? So we can do any digital function of 3 inputs and 2 outputs, right? We've got some programmable multiplexers. So we can then, again, according to the configuration of this thing, the output for that initial LUT stage can be directed either, well, it goes to this FA, it's a full adder, so it's a full single bit adder, so it does, you know, it does a single bit binary addition with carry, right? And you can see the carry comes in and the carry comes out, so you can imagine how these things might get chained to build, you know, proper wide adder structures, for example. We can then choose whether the, you know, this input D just sort of gets routed around and comes in. We've then got a D flip-flop. It's the most simple register or memory element in a digital circuit, right? So what a D flip-flop does is when the clock goes high, so here's our clock signal coming through here, it just latches or registers the value on the input, right? And then presents it on the output. So this is a single bit of memory. So we can either take the output from this logic cell from the D flip-flop, or again, depending on how that final mux is configured, the output from that sort of third stage can be passed directly through. So in a single configurable logic block, we can implement arbitrary, either sequential or registered digital functions of sort of 3.5 inputs, optionally with a carry and optionally with a clock, right? You can't do much with this, right? You can make like a 3 input AND gate, OR gate, XOR gate, or whatever. But when you have now the first Xilinx FPGA, my talk is heavily Xilinx focused, right? It's where I spent all my career. I'll try and mention the competition as well. They're not paying me. There's no favoritism there. I'm just talking about what I know. First Xilinx FPGA, I think, came out in 1985. It had 64 of these things, right? And embedded, I think maybe I've got a slide that shows it. These things are embedded in a fully programmable bit granular switching fabric. So we can direct the output of just about any logic block to the input of any other logic block, and we can fan it out, so we can have one output that fans out as an input to multiple logic blocks, right? We've got a global clock network, so this clock signal, which will, you know, typically be coming from an oscillator on a circuit board, this clock signal can be propagated throughout the device. Modern FPGAs have tremendously sophisticated and complicated clocking capabilities, but, you know, the principle's the same. So we've got a sea of these things, programmable things, embedded in a sea of bitwise granular switching fabric. You can implement with this and the switching fabric any arbitrary digital function. That could be a 32-bit adder, or it could be a microprocessor. Right? Microprocessors aren't magic, they're just digital logic, lots of registers, lots of lookup tables and so on. And they're limited only by the capacity of the device, how many of these things you've got, and how fast you can clock them. All right? That is the essence, at the core, that's what FPGAs are. All right? So, there is more to the story. So digital logic is a, you know, fundamental kind of essential necessity. We've got to have it. But there's a lot more to it than that. So chips need I/O, right? We need to be able to run signals to the outside world. And so we end up needing to support things like different voltage standards, different drive currents, different termination resistance, all these kind of electrical and timing properties of the I/O. And we need to be able to handle clocking. Memory is a very useful thing. So you can simulate memory, like, you know, SRAM with address lines and data lines and write enables, read enables. You can simulate RAM by just tying lots of these together and configuring in a certain way, but it's a very inefficient use of these logic resources. So one of the next kind of obvious innovations in FPGA design was to include dedicated blocks of typically dual-ported RAM. So SRAM, it's dual-ported, I mean you can read and write, it's got address and data lines on both sides of the device, right? So you can read and write simultaneously. These are really, really useful because you can use them to build things like first-in, first-out buffers, You can use them as just normal kind of randomly addressable memories. You can do all sorts of stuff with them. And of course, you can kind of glue them together digitally to simulate larger memories, either bigger address spaces or wider data spaces, right? So-called block RAMs. I think, are there even SRAM blocks? Where are they on this diagram? I don't know, the colors are a bit washy. I think they're those green things in there. I stole this one from DigiKey. So this was cool. So we're kind of developing, we're a couple of years into the FPGA sort of revolution, I guess. And of course, what happens is people start designing with these things and they're falling in love with the technology and the capability and the flexibility and all this kind of stuff. And they start to run out of logic blocks, and then Xilinx and Altera and the smaller FPGA vendors kind of do an analysis of the sort of designs that people are building with these devices, and they're like, oh, that's interesting. We've got a really big market segment over here that want to do high-speed DSP, and everyone's burning their entire chip building multiply accumulate chains, right? FIR filters, this kind of thing. So they design a general purpose DSP engine, and they put them in here. Again, connected into the fabric, configurable, so you can tweak, you know, all sorts of parameters, but at its heart, it's a multiply accumulate block, right? And then, you know, we started to enter the period. I mean, you guys were mucking around with USB-C, you know, tonight to get all the AV working. And of course, as soon as you start doing high-speed processing workloads, you need to get data in and out of the chip really quickly. So we now start to move to things like gigabit serial transceivers. The other real benefit of that stuff is that pins are expensive, right? Pins on a chip are incredibly expensive. They take up real estate, they take metal, they take, you know, the little micro gold wires that kind of lead everything out from the wafer to the package. So if you've got sort of high bandwidth data, I don't know, 32, 64-bit wide, and you've got to burn 64 pins just on that channel, you quickly start to run out of real estate. So these single-bit, high-speed serial links have basically taken over everything, right? HDMI, USB, Thunderbolt, whatever, right? So putting hardware support, I don't know what color these are, SerDes, serial deserializers, so these little pink guys here. Putting serial transceivers on these chips then gives hardware designers the ability to do lots of really fast I/O. Okay, and they just kept going over the last, almost 30 years, I guess, these devices. I'm not going into the ancient history of programmable array logic and all that sort of stuff, but it's got its origins there. CPUs were the next thing, and we'll come back to these tonight when we talk about that. So, as I said, you can build a CPU out of general purpose logic if you want to, but it takes a lot of it, right? CPUs are pretty complex digital circuits, particularly ones that have useful stuff like caches and deep pipelines and, you know, branch prediction and all of these fancy things that computer architects have come up with over the last 50 years to make things go faster. So the FPGA vendors go, right, let's make a family of these devices where we just dedicate a little bit of the silicon and we put a fully formed CPU in there, and we put the little stubs there so we can connect it into the fabric. I probably should have mentioned, there's about a 10-to-1 efficiency cost in terms of transistor count, in terms of implementing something in dedicated silicon, right, just manufacturing the transistors directly on the die, versus the number of transistors required to create the configurable logic blocks and all the switch fabric and then configure them to do that function, right? So really what I'm saying here is that if a CPU takes up, you know, this much area, if it's dedicated transistors on the die, it would take roughly, it depends, but roughly kind of 10 times the number of transistors to do it out of programmable logic, and it would be slower. All right, so this is the first lesson. Dedicated silicon is always faster, it's always lower power, and it's always smaller. All right, so we've moved then to these kind of hybrid things where, you know, there's this large sea of programmable logic and then a heterogeneous mix of dedicated blocks. So CPUs, we now have devices that effectively have kind of AI, ML style sort of inference engines on the in the die, right? And you just kind of wire them in, provide the coefficients, stream your data through, you get your high performance inference coming out. So these are the new hotness, and I'll show you a block diagram. I think I've got a block diagram of one Xilinx. I'm not sure what the competition are doing. Now also have ones that have RF, radio frequency interfaces on these things, right? So they've got 4 gigasample per second radio frequency digital to analog converters on the device, so you can bring your analog straight to the package and digitize it, and do all your intermediate and baseband processing and stuff, right? So, these are not your grandfather's FPGA anymore. So here's just one example. I'm going to skip over this. This is a rough block diagram of the Xilinx DSP48 block. So this is a generic multiply accumulate block. All right, takes a number of I think maybe they're 48-bit inputs. I'm not sure, to be honest. So it's got a couple of register stages, so you can pipeline your design, so you can clock it faster. Don't have time to go into the details of that. There's the multiplier at the heart of it, and it's got various pattern detectors. So with these, you can then, so in this case, the FPGA configuration, the multiplier is already there and the adder is already there. The FPGA configuration instead just kind of tweaks, which of the mux channels are selected, or, if the pre-adder is used, or, and so on, right? So now, with a relatively small number of transistors and a relatively small amount of configuration memory, we can build, really high performance kind of multiply accumulate chains for doing things like, very, very high frequency filtering, for example, image processing, image filtering, all that sort of stuff. So that's just one example. Right, so the first Xilinx FPGA, I had to Google this, had 64 CLBs, complex logic blocks. And that was considered to be roughly about 9,000 equivalent logic gates. The latest ones, and I had to Google that, roughly 4,000 logic cells. Now these CLBs are different now. They're more sophisticated, they're more complex, but it's the same idea. It's just the evolution of it. So, roughly 4,000 logic cells, up to 13,000 DSP blocks, right? So 13,000 individual high-speed pipelinable multiply accumulate units. So, we're talking the kind of DSP capability you need to do very high frequency, kind of radio processing radar. So these things are used in a lot of modern multi-channel radars, for example. It's got 450 megabits of embedded RAM, so you could boot Linux just on one of these things. And then plus all of that other stuff, right? Hundreds of programmable IOs, CPU cores, other special purpose blocks. So these are pretty wild devices these days. So that's awesome. I can buy a device like this from Xilinx, and it's got all of this capability, right? There's a big question though. How on earth do you program this thing? How does a designer or a design team in reality actually reckon with the complexity and the power and the capability that is in here? So in the very, very early days, it was manual. So for, predating FPGAs, and I think I remember studying this in my engineering degree actually, there were these kind of sheets that you would get that represented the logical structure of this programmable device, and you would manually work out how to connect the registers, how to route the signals, and you kind of fill them in with pencil, and then there was some way of transforming that into the equivalent of a bit stream. You could program these devices and off you went, all right? You obviously can't do that for modern devices. Anything over, a pretty baseline level of complexity, that's just not tractable. It's not possible. So there were a few iterations. Eventually, we came up with these ideas of hardware description languages. So they're programming languages. They look like software, but they're not. They're a textual description of a hardware circuit. And this trips up a lot of people, and it tripped me up. First time I saw an FPGA, I was like, sweet, there's a for loop. I'm just going to use a for loop A for loop in a hardware description language isn't iterating over time, it's iterating over space. It's instantiating multiple instances of whatever little bit of circuit is described inside the for loop, right? It's a really classic trap for young players in the HDL space. So there's two main ones now, VHDL and Verilog. There are religious wars about them. I don't really buy into that. The modest amount of digital design I've done is with VHDL. Verilog, I think, is a bit more dominant in the US electronics industry for various reasons. And there's modern iterations of these and modern standards. Excuse me, let me mute that. Right, so here is an example of, a very simple example of some VHDL. It is describing a hardware structure. In this case, it is describing a thing called an entity with ports. And there are two inputs, input 1 and input 2, and there's a single output. So these are single bit signals. So we define the interface to this thing, and then we define the architecture. That's the actual substance of it. And in this case, don't mind all the glue and guff around it. It's basically saying, well, we want to drive this output, this signal here, AND gate. We want to drive it with the value of input 1 bitwise, or logically ANDed with input 2. And then we're going to assign this internal signal to the output. So this is a 2-input, 1-bit output AND gate described in HDL. Now, this is still pretty low level, but now we have the ability to start using abstraction, right? So we design the smallest, kind of lowest level components in the system, and once they're tested and verified, we can then start to assemble them and wire them together. And it's through this kind of HDL style design flow that it was made possible for doing, and VHDL and Verilog, by the way, are used for ASIC design as well, right? It's not just FPGAs, it's the same languages, very similar tool flows. But it was through these kind of tools that it actually became possible to program these things at all, with designs of any reasonable and, in fact, in many cases, mind-boggling complexity. It's still not easy, right? For software people coming to hardware description languages, it's a completely new mindset, right? You've got to get out of that. We're used to writing programs and, this line executes, then this line executes, and then this line executes. That is just not the case. It's a textual description of an electronic circuit or a digital circuit. By the way, first plug for the evening for CSSE 4010, taught by my colleague Chamith. We used to teach a lot of this stuff here at UQ. We had a pretty strong kind of digital group, Neil Bergman, Adam Postula, myself, a few other people. The sort of, I guess, priorities and feedback from industry advisory boards and all that sort of stuff had changed a little bit over the years. So in my opinion, we don't teach as much of this as we should, especially given the relevance of this to the Australian industry. That may change one day. But for now, yeah, CSSE 4010, and I don't know what the prerequisite chain is for that, I'm sorry, you can look that up. But Chamith does an introduction to this stuff. He also does an introduction to some of the reconfigurable system stuff that I'm talking about as well. Oh, yes? Yeah. How does this get converted into a circuit? Excellent question. So this thing gets converted into, there's multiple steps. It gets converted into something called a netlist, which is really just a binary description of the circuit, resolved down to the simplest kind of non-synthesizable elements. So this one might just resolve down, so like an AND gate is a sort of a fundamental primitive. So this would resolve down to a very simple netlist. It then goes that's when the path for ASIC design versus FPGA design diverges. It goes through a process called mapping. In this case, the fundamental elements of the netlist, the adders, but also maybe the DSP blocks or, any of the complex blocks and all the connectivity between them, gets mapped onto the available kind of fundamental logic primitives in the device. So in this case, this thing would be mapped onto, one of those lookup table type structures that we saw in the, one of the early slides. So this is technology mapping. It's taking this generic net list, which is just a circuit description, and mapping it onto the available digital primitives that are on the device. It then goes through something called place and route, which is a tool which takes that mapping, which says, all right, well, we need a DSP block and it's configured this way, and we need a block RAM, it's configured this way, and we need 1,000 logic blocks and they're all configured this way, and this is how they're all connected. And it figures out, and it's got this database of every device and what resources are there and where they are on the chip, how they're connected, how quickly signals can propagate between them, like all of these really fine-grained physical properties of the device. And it says, all right, well, this design needs a DSP block, so we're going to put it here on this one, and we need a bunch of CLBs, and they're going to be configured this way, and we're going to put them here. We're going to configure the switching fabric to get these signals into the DSP block, right? That's called place and route. Place and route, then the output from place and route then goes into the final process for FPGA stuff, which is bit stream generation. So that takes this direct physical kind of mapping of the logic circuit and the FPGA primitives, and it produces a binary file. It's just a bunch of ones and zeros, and that's what gets loaded into the FPGA when the power is turned on. That configures the, can I do this? No, I can't. I don't know what's happened to my laptop. Anyway, I won't skip back. That configures the RAM cells that are sitting, if you like, kind of behind the logic plane, right? So a 1 here means that this mux is switching that way, and a 0 here means that this lookup table is configured in a certain way. That's the thing which gets loaded into the FPGA. So it's a multi-stage tool chain, just like compiling software. You've got compiling, linking, and so on. It's a multi-stage tool chain. That's it in a nutshell. Good question though, I completely glossed over that. All right. Wakey PowerPoint. Okay, cool. So that's kind of FPGAs in a nutshell. So we're going to pause there a little bit, and I'm going to start to talk about CPUs. And in particular, this tension between CPUs and FPGAs, right? So CPUs are amazing, right? You don't realize it. Maybe you do if you pay attention to me in 2310, but CPUs are incredible, right? You can write a 3-line program like this and compile it and link it and run it in some kind of environment, whether it's an operating system or an RTOS or whatever, and you can get stuff to happen really, really easily, right? And we're so kind of embedded in the software paradigm, and we've got all these wonderful portable languages, so we can write this program once and we can run it anywhere from on my watch to probably that camera, my laptop, your phones, to supercomputing clusters, right? So the portability of software and the things that sit underneath it, operating systems, is incredible. I know there's a couple of you enrolled in 2310 this semester, so here's the multi-core version of Hello World, right? And again, we can trivially spawn multiple threads, make use of multiple CPUs. Hopefully you've done your locking and your data structures right, and now you've got a program that is able to make use of multiple CPU cores, right? So the productivity of software is just impossible to beat, right? And that is the legacy of decades of research and development and language design and standardization, operating systems standardization, design and standardization, and so on. You can just do stuff so quickly in software. And this is C, right? What if we're doing this in Python, right? You can write a 10-line Python program that, trains an ML model if you want to now, if you pull in the right libraries, okay? So CPUs are awesome. CPUs suck. Right, this is a very old graph. I pulled some new data. I didn't make this graph. I pulled some new data yesterday, but I ran out of time to crunch it. And if anyone's interested, I'd love to work with you to update this data. So this data is like 15 years old. Doesn't matter. The point remains. So here we've got roughly a time axis, and these are some archaic. You guys were probably all in kindergarten when these were contemporary CPUs, right? That's fine. I had one of these, a Celeron 300. It was a famous Celeron that you could overclock to 450 megahertz, and they were really cheap. So we all had them to play Unreal Tournament. The y-axis is what's interesting about this graph. Look at the units here. MOPS, so million operations, per megahertz per million transistors. What does that mean? What's that unit mean? It's the number of operations, probably integer, the number of operations normalized with respect to the clock frequency and normalized with respect to the number of number of transistors that comprise the CPU, right? This is a measure of how much overall contribution each transistor on the chip is making to our computation, right? And it dropped precipitously and leveled out. And honestly, I've got a really interesting data set. It'd be very interesting to see what happens happen over the next 10 years. Just didn't have time to crunch it. What is this saying? This is saying that as CPUs got faster and more powerful and more cores and bigger caches and deeper pipelines and better branch prediction and all those things that we do to make CPUs fast, the individual transistors are actually contributing relatively less to the computation, right? So even though, I mean, okay, there's also things like semiconductor process shrink taking place over time, right? The transistors are getting smaller, we're reducing the voltage, so we're making the individual transistors more efficient, but on a per transistor basis, CPU architectures are actually getting less efficient, not more. It's just we pack more in and we clock them faster and we cool them better, right? And we can see this when we have a look at a diagram of a generic 32-bit CPU, all right? So this was, I don't even know if this website's still here. I made this example a long time ago, but it's still accurate, right? So this is a pretty standard block diagram for your generic kind of entry-level CPU, right? And with a bit of work and a bit of practice and a bit of good luck, you could probably learn enough VHDL to build one of these yourself, right? Question. So we're talking about computation, right? We're interested in transforming numbers. We've got data coming in, we want to do something to it, and we want to get data out, okay? That's what computation is, whether that's radar processing, image processing, medical signals, whatever. Where does the computational work happen in this diagram? Right, it's in the ALU, the arithmetic logic unit. So this is a thing that does additions and subtractions and multiplications and maybe divisions, and maybe we might have a floating point unit in here, okay? So this here, these are the only transistors in the CPU that are actually contributing to doing the number crunching, right? All of this other stuff around here, right? We might include the register bank actually if we're feeling generous, right? That's our temporary storage. But all of this other stuff is interacting with memory, right? We've got to fetch instructions from memory. We've got to decode those instructions to actually figure out how to configure the ALU on an instruction by instruction basis, right? We've got to get the results out of the CPU into memory, okay? Now, I was too proud to include the screen, the shot that used to follow this slide because it was a die shot of again, an obsolete CPU, like a electron microscope photograph. But what you could see was that of all of the real estate on this thing, the ALU, it was a 6-core Intel something or other. The ALUs, the places where the actual work took place, were a tiny, tiny proportion of the transistors on the device. And everything else is just glue to get data to that ALU as quickly and efficiently as possible. And also other really complex stuff. Pipelining the CPU. I mean, I think a modern Intel architecture has like 100 pipeline stages, something like that, right? So, you kind of, if you look down at the assembly level, you see instruction, 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 but what actually happens, and we've got multiple issue. So there's, tens up to, I think, 100 or so instructions in flight at any one time, doing things like branch prediction, trying to figure out, are we going to take this jump? If we are going to take the jump, we can throw out all the temporary values that we've been sort of calculating to try and predict the results. So there's this incredible complexity in a CPU, all just there to try and get values in and out of the ALU as quickly as possible. All right, so they're really inefficient in a hardware use. What's my next slide? Okay, so Everyone who discovers FPGAs, every young engineer who discovers FPGAs after living a life of software, they go, oh my God, these things are incredible, right? I can create these special purpose circuits and I can clock them at, you know, tens or hundreds of megahertz. And hardware is intrinsically parallel, so I don't have to worry about sort of sequential processing. I don't have to worry about how many cores I've got in my CPU. I can do everything in parallel at once on the chip, and I'm going to design the fastest circuit ever, and it's going to be amazing. And this is all true, right? And so again, I've got a slide. So FPGAs and digital logic generally, we're talking about FPGAs, have this tremendous kind of latent capability, this incredible intrinsic bandwidth within the fabric, this incredible intrinsic kind of compute capability, because we can, you know, we can configure the entire FPGA to be just number crunching, you know, stream the data in, crunch, 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 stream it out, right? We don't need all of that other junk around the outside, always. And so a bunch of people did a bunch of work. Again, this is old news now, but it's sort of comparing CPUs. Here's a dual core CPU, quad core, 6 core, and honestly, this graph is going to be 10 years old minimum. So there'll be newer versions of it, and they test them on various workloads. And what have we got? Raw gigaflops here. So for any given computational algorithm, it's almost always you get a faster result by creating special purpose hardware for it. That's the takeaway, right? So FPGAs are awesome. We should just do everything with FPGAs. That's what everyone who ever discovers an FPGA goes, oh my God, I'm never going to write a line of software in my life. Certainly happened to me. FPGAs are awful, right? They're horrible. There's a reason they call it hardware, right? Designing complex systems at bit level granularity, where you, the designer, are responsible for the movement of every bit of data from one part of the circuit to the other, right? Makes you wish for Hello World and the standard C library, right? You get this tremendous flexibility, this tremendous power, and it's all your responsibility, right? You've got to do all of it. You and the team of hardware engineers that you're amongst. And this is because hardware design is traditionally performed at this incredibly low level of abstraction. I'm going to skip over this. This is a sort of hello world in VHDL. It takes a 200 megahertz clock in, and it divides that clock down to a slower clock and blinks an LED. All right? And that's cool, but imagine designing a high-speed DSP processing pipeline with something like this, right? So that design model is really, really challenging. All right, I better get on with this. We're going to be late. So in fairness, right, as the FPGAs have got bigger, the tools are much better, right? So we have now pretty mature tools for things like going from Simulink. Anyone's used MATLAB and of course, you're all robotics people. Of course you know what Simulink is, right? So going from Simulink, you know, asterisks, not generic Simulink, but, you know, many of the modules in the Simulink library, and you can just push a button and it will just generate hardware for those circuits, right? So this is pretty cool. People use this a lot. There was, and probably still is, a tremendous amount of research going on in high-level synthesis tools. Why can't I just take my C code and crank it through some tool and spit out VHDL? This sort of so-called C to gates. And a lot of people spend a lot of time and a lot of effort and a lot of money trying to do this. And if you think about a C program, a semicolon is kind of like a clock tick, right? You know, each statement you terminate with a semicolon. You can kind of imagine that like a clock of time passing through. So the idea is you kind of synthesize, you know, each line of C program into an equivalent circuit. Oh, we're doing, you know, A equals B times C. Awesome, we'll instantiate a multiplier. We've got these signals A and B, and right. Turns out it doesn't work quite like that. What does a pointer mean in VHDL, for example? Or a function pointer, my God, you know. So I don't know this for sure. I don't know if it's provable, but it's incredibly hard, if not impossible, to do in the general case. So, but there are limited subsets of C, you know, like the tight loop in your DSP algorithm or your robotics control algorithm, that sort of stuff that can sort of feasibly be turned straight into hardware. And so there are commercial versions of all this sort of stuff, and there's a few open source kind of experimental ones. You know, the big thing is modular and component-based design, right? So when you sit down to design a very large complex circuit, you look to libraries of existing components, right? You don't build everything from scratch in the same way that when you write a C program, hopefully you're not rewriting the standard C library and not re-implementing printf, okay? So there's, you know, the vendors provide standard libraries, and then there's a whole ecosystem of companies that provide and sell libraries of so-called IP cores, intellectual property cores, and in principle you just kind of drop them in, connect them up, and they just work. They give you a data sheet, just like an electronics component that you put on a PCB, you get a data sheet for a virtual component. Signals in, signals out, how you configure it, how it performs. So that, you know, that helps. And then we get sort of application-specific automated design tools. So this is really hot now in the AI inference space, right? So everyone wants to do edge inference, right? They want to run, you know, they want to train their machine learning models somewhere in a data center. They want to get the weights out of that model, and they want to put them on a small little device. So NVIDIA's Jetson, you know, devices were really popular for a couple of years. They probably still are. And Xilinx and the FPGA vendors are all kind of running after that market too. So there are kind of, you know, these are well-structured, regularly kind of shaped computations. So when you have that, it sort of gets a lot easier to automate and simplify that design. But it's still pretty hard, right? I'm working with a company who's got a really critical bit of logic in their system that was designed by a genius 10 years ago, who no longer works with the company, and nobody in the company really understands this bit of logic. He's actually implemented his own sort of custom CPU. He wrote his own compiler. This is what happens when you let geniuses loose on real engineering projects, is they do things like create their own CPUs and write their own compilers. Anyway, this is a core bit of technology for the company, and actually they just dare not touch it because they don't really quite understand how it works. Okay, and there's probably plenty of software out there that looks like that too. Anyway, moving on. So, of course, the answer is not CPUs are better or FPGAs are better, right? And this is the motivation that drives reconfigurable system on chip. So, let's use CPUs and software for the things that CPUs and software are really good for, and let's use digital hardware and FPGA fabric for the stuff that they're really good for. So this is where Neil Bergman and I started in 2002. Xilinx had just released this thing called the Microblaze, which was an IP core, so just a logical digital design, targeted their FPGAs, and it was a 32-bit CPU. And Neil had a bunch of postgrad students and we were trying to do all sorts of experiments with this stuff. What can it do? What's it good for? What are some of the good models for integrating hardware and software and, you know, all that cool stuff. The software stack was pretty awful. It was this kind of low-level RTOS-ish kind of standalone environment. It was all pretty awful. So Neil said to me one day, why don't you port Linux to the Microblaze? And I was like, yeah, sure, how hard can that be? Yeah, that was a good time. So that took me about 6 months. I'd never used Linux before, let alone looked at the kernel. The toolchain was full of bugs, so the compiler was all full of bugs that hadn't been properly tested and shaken out. So what I did is I found another 32-bit CPU architecture, this thing called the V850, that architecturally was quite similar to the Microblaze. And those of you might remember from 2310 when I show you that diagram of the architecture of the Linux kernel, I said there's hardware-dependent stuff down the bottom here. It's all written in assembly. So I translated instruction by instruction about 1,500 lines of assembly code from one architecture to another, but also figuring out, okay, well, they use these registers for this purpose, right? And miraculously, it sort of worked, right? So the lesson is there, just because you don't know how to do something doesn't mean you shouldn't give it a go anyway, because if I had any idea how hard this would have been, I just would have said, no, you're crazy. You know, to Neil's credit, he was very patient with me, and I learned a lot. So we got Linux, or a version of Linux that doesn't require virtual memory and memory management units, which existed at the time, running on the Microblaze. So that was kind of 2002, 2003 timeframe. Now there's another really big challenge, and this is actually where a lot of the value in the business that I subsequently made out of this came. So take a look at the microblades, right? You can configure, this is one of the nice things about it, when you instantiate it, when you synthesize it, you can configure, like if my software doesn't need the multiply instruction, we can just configure the CPU to not have it, right? So you save all of that logic because we don't need it. And similarly, if you don't need an instruction cache or a data cache, just configure it out and it's not there, okay? And this is great. So this thing, you know, the sort of, even the first generation of microblades, there were probably something like, you know, some power of 2, probably around 512 possible combinations of all of the parameters that you could configure this thing in, right? And we had to write software. And then of course there's all the peripherals on the outside, right? So UARTs and Ethernet controllers and blah, 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 all of which could all be configured as well. So we had this sort of massive dimensional configuration space. And the question was, how on earth do you configure an operating system as complex as Linux when because the whole point of using an FPGA is that every single design is different, right? You include the peripherals you need, you include the CPU features you need. So every single one of them is different, and it's coming out of a design tool that we get from Xilinx. How on earth do we actually get all of that information into Linux to configure that so that Linux actually runs? We've got to compile the Linux kernel with or without the mul instruction, with or without the div instruction. We've got to use or not use the caches and so on. That was a really interesting problem which we solved pretty comprehensively. I don't have time to go into. You might be asking why Linux. This was a very, very long time before I taught CSSE 2310. And it's pretty much summed up by this quote here. This is an early pioneer in embedded Linux, right? When Linux was sort of making the jump from desktop server environments down to really small devices. It's a guy called Jeff Dion. And he said, Linux is the C runtime, right? Linux is just the software stack that programmers of software of any reasonable sophistication just expect to find. Okay, that's why, you know, void main, printf hello works on pretty much any machine. Okay, the program is tiny, but you've got the standard C library, you've got the system call interface, you've got all the drivers that get those characters either to the terminal or over a network socket or through a pipe or whatever, right? So Linux is the C runtime. So this is standard libraries, standard operating system interfaces, the full network stack, memory management, process schedulers, you know, threaded support and all that sort of stuff, right? So the argument was that if you can get Linux running on these devices, then all of a sudden that developer productivity goes back up through the roof. You're no longer responsible for everything. And the other thing it's got is a vast ecosystem of open source software, right? So you don't need to write your own web server. You don't need to write your own FTP servers, you know, SSH servers. I'm thinking all of network applications here, you know, network time clients, database systems, whatever, right? All of this stuff comes more or less for free. So Linux made a lot of sense. So that's what we did. So the first hack port, you know, instruction by instruction took 6 months. I learned another really, really valuable lesson. When you are porting a well-established, mature piece of software to a new architecture, a new platform, whatever, every bug is yours, right? And it took me a few times posting to the kernel mailing list or the variant of it that I was active on, saying, oh, you know, and this isn't working. I think there's a bug in, you know, some generic Linux system that's been used by hundreds of people over tens of years. And the answer is always no, the bug is always yours, right? So it's a pretty humbling experience. I started a mailing list because it's an open source project. I thought I might get some help. Found lots of bugs in the Xilinx tools and the compilers. That was good, but made some good relationships with the engineers at Xilinx in the process. And then a really interesting thing started to happen. People joined the mailing list and I didn't get a whole lot of help, but people started actually using this thing. All of a sudden there was this interest in running Linux on the microblades. First time I told Xilinx that's what we were going to be doing, we said, no, you don't want to do that. We've got another FPGA that's got a hard, you know, a PowerPC CPU core on it. Don't worry about the microblades. I'm like, yeah, we'll do it anyway. People started using it. So I got an email one day, 2004, from a research project director at NASA Langley Research Center. He's like, hey, we love your stuff. We're doing this project, Reconfigurable Spaceflight Computing. We want to build these stackable, configurable modules and pre-qualify them for spaceflight, and we want to use your stuff on it. I'm like, sweet, let's do it. So we got like a $16 million, we were part of like a $16 million research grant that looked at, you know, they built some hardware, we did some really cool stuff. And why that was really important was because all of a sudden, I had this kind of loosely cobbled together kind of way of building Linux systems for Xilinx devices. But now I was the software lead on this project, and there were going to be other engineers who actually had to use this stuff and do useful stuff with it. So the usability of all of that tool flow really started to matter. It was no longer okay to kind of run one tool over here, you know, edit the output of it, copy it over here, do some manual steps. So I had to start developing and solving some of these problems like, you know, infinitely variable hardware. How do we get that across to the software? So for me, the most valuable thing that came out of that was not actually technology, but a focus on usability, making the tools good enough so that they were easy for people to use. Because if you make something easy for people to use, they'll use it, right? So never forget about how important tools and usability are. Then around 2005, a pretty similar time actually, Xilinx called in. They're like, "Oh, hey, John," it was like a marketing manager. I used to speak to their engineers all the time. I got a call from one of the marketing managers, and he's like, "Oh, hey, yeah, we got these customers using this Linux thing of yours. Where do they go for like commercial support and stuff?" And I'm like, "Oh, I don't know." And they said, "Well, can we send them to you?" And I'm like, "Yeah, all right." So I picked up the phone, called UniQuest, and said, "Hey guys, can we do consulting stuff?" And they're like, yeah. The guy at UniQuest had just been to a seminar from Red Hat's CEO. He was all fired up about open source business models. So we registered a business name, Pedalogics, and we were doing really, really simple stuff. Basically just little bits of consulting, helping people understand the technology, writing a few device drivers, that kind of thing. And this all happened because, well, I got kind of lucky, right? This stuff was useful, but I ran a mailing list. And so I got a community involved and people kind of engaged with it. And, you know, I had a lot of freedom and flexibility to kind of port that mailing list. So I was very active there. And then other people sort of got skills and got active. We built a community, right? But then when an opportunity came along, when Xilinx said, "Oh, can we send business your way?" I was like, "Yeah, all right." So we took that opportunity. Oh my God, look at the time. We're getting there. So this started as a consulting activity here at UQ through UniQuest. A couple of years later, I realized that I couldn't run a business at UQ and also be a decent academic. I'm more of an engineer than an academic, but well and truly. So I spoke to the university and I bought the intellectual property and the trademarks and all that sort of stuff. Pretty cheaply, as it turned out, because there wasn't much use to them without me. So I spun it out, started a company, and again, just continuing doing mostly design services. But that work I'd done for that NASA project about making usable tools and really making a good flow so that anybody could use this stuff, and they didn't have to be a kernel hacker, right? We had just nice tools. They could they could design their system in the Xilinx tools. They could export that description to our tools. And then with a pretty modest amount of work, like we got so good at this internally in the company, we could bring up Linux on a brand new board that we'd never seen, in an hour, right? However it was configured, all this kind of stuff, some caveats there. But those tools were really useful. So then, about 2009, I was working really closely with some of the marketing people at Xilinx, and they're like, "Hey, we're releasing this whole new line of FPGAs, and we want to support Linux on all of them, and we want to ship demo images of your stuff on every board that we sell," right? And I'm just like, "Oh my goodness, that's incredible. It's a lot of pressure." But he said, "Look, you need to kind of commercialize these tools, these Petalinux tools, because we've been giving them away for nothing, right?" And I was like, "Oh, okay." So we did that. We did some engineering, and I hacked together. So the original version of the Petalinux tools were written in shell script, right? That's the joke I make in 2310. I wrote about 5,000 lines of, if you can believe it, object-oriented shell script in Bash, right? And all of a sudden I wanted to ship this, and I wasn't willing to learn Python at the time. I should have, but I didn't. So I found this tool that could obfuscate shell scripts. So that was the first version of Petalinux. It was just these weirdly obfuscated shell scripts. It sort of took the shell script, encrypted it, bundled it as a payload in an executable that then decrypted it and executed the shell script, right? That was my copy protection mechanism. And our licensing mechanism was doing a MAC lookup against a web server that I administered, right? You just make all of this stuff up as you go, right? We built a customer support system out of some open source components. I just hacked it together over a couple of days and launched it, and it kind of worked, right? So that was amazing because now everybody who bought one of these boards got a little flyer in the box for our stuff, and the tools that I've been giving away free, we were now selling for $5,000 a seat, right? Specialist engineering tools, make this really easy kind of return on investment argument to the engineers. It's like, we've got to save your engineer like 2 hours a week over the course of the project, and these tools are paid for themselves. And the customers came. And that was awesome, because going from consulting, where to bill an hour, you've got to work an hour, right? Consulting's great when you're getting a business started because you don't have big expenses, right? You just need a customer who's willing to pay your hourly rate. As soon as you've got a product, you can just kind of crank the handle and sell another one. And when it's software, it's even better. You just generate a new license key, email it to them with an invoice for $5,000. And now you start to got some sort of capital. You can invest in improving the features, maybe rewriting the software in Python instead of shell script, whatever. Anyway, so that's my little kind of exciting time in business. This was all in microblaze land. 2010, Xilinx came out with Zinc. I'm going to have to skip over this block diagram, but Zinc basically has two 32-bit ARM cores, full MMU, full Linux capable. It's got a bunch of programmable I/O. It's got a bunch of really interesting I/O devices. It's got USB host controllers. It's got UARTs, all sorts of stuff. And they said, we want you to make your tools work with this architecture. And we did. So when this chip was available in the market, we had full support for it in Pedal Linux, and all of our development flows, all the documentations, all that sort of stuff was there. We also did some cool stuff with emulators and virtual environments and stuff. All right, I better wrap up because I've got a bus to catch. Okay, so last couple of slides. So by 2011, we were 8 full-time engineers. Pretty much all of them were just my former students. This is my trick, right? You offer them a thesis project or a master's project in the technology. If they're any good, you give them a job. Worked really well. Keep that in mind in future. We were maintaining the Linux kernel upstream, the GCC toolchain, GDB, and also this QEMU emulator platform. That was a commercial contract for us to do that. We were contributing to open source products, big projects, and we were delivering tools and services to Xilinx's biggest and small customers. So, Intuitive Surgical, they were one of our first customers. They're the guys who make the Da Vinci robot, right? So our stuff was in that. I got to play with one of those in San Jose. That was really cool, very cool tech. I did some work for GCHQ in the UK, and I met these two kind of nerd tech spy guys in the lobby of a hotel in San Francisco, and they kind of, they might have been wearing trench coats, right? And we did some very generic technical work for them, but they loved the cloak and dagger stuff. Cisco, Alcatel-Lucent, Intel, so we were doing all sorts of stuff. We'd become a critical part of Xilinx's supply chain. So when they've got a company like Cisco who's maybe spending $10 million a year, $20 million a year on chips, and they're relying on tools and services from this little company down in Brisbane, they start to get a little bit nervous. So that's when we started talking to Xilinx. And in 2012, they bought us because I didn't want their money. I didn't want investment. I was like, nah, you can buy us. So we all then became Xilinx employees. We set up an office here in Brisbane, and we became their open source system software group. And that was a pretty interesting time. And I could tell lots of stories there, but I don't have time. Where are we now? Okay, Intel bought Altera in 2015. AMD bought Xilinx last year, right? I wish I'd held on to my Xilinx shares. But anyway, and they're just rocketing down this road. So this is the MP-SoC. This is more or less Xilinx's latest version. It's got 4 64-bit ARM cores in it. It's got 2 32-bit real-time cores in it. It's got full hypervisor virtualization support. It's got all of the security stuff. It's got secure boot. It's got all sorts of jazz. All of this connected into, a large sea of programmable fabric, high-performance memory ports, all this sort of stuff. I mentioned the RSoC, which is one of these, but it's also got radio frequency, multi-gigahertz digital to analog, ADCs. analog to digital converters, right? So you can connect these things directly into an RF backend. The design complexity on something like this is just mind-boggling, right? So the first thing you do is you boot Linux on it, and then you figure out your hardware architecture, you figure out how you're going to glue it together. Okay, last slide, I promise. Why, and look, I do apologise for having to be so shallow on the technical stuff. Like I said, we could do it, we could do a full semester course on this without touching the sides. Why are these devices such a good fit for the Australian electronics industry? I mean, I'm biased because I move in those circles, but I know it's true. Has anyone heard of a company called Blackmagic? Melbourne-based company? Yeah, of course you do. Is that no, it's not a Blackmagic camera. But they're full of Xilinx FPGAs, right? Why? The economics of semiconductors. Right, so fabbing your own silicon is really, really expensive. And I just Googled this, so I might be slightly wrong, but at 28 nanometers, which is a pretty obsolete kind of process node these days, costs about $1.5 to $2 million for a mask set. That's the set of masks that are used to expose the silicon wafers and do all the etching and all that sort of stuff. And then depending on packaging and wafer size and all that sort of stuff, there may be a few dollars, $10 each after that. But you've got to spend $1.5 million to get the first one. Lots of Australian electronics companies are producing low volume, high value products, meaning that they're not selling at the cheapest in the market. They've got very clever products, lots of intellectual property in there. They do really innovative things. Companies like Blackmagic, companies like some of the other ones that I work for. So cost is always important, but it's not the prime driver. Features and the ability to kind of iterate and innovate. And this is why FPGAs in general, but actually this Zinc and reconfigurable platforms in particular, have had so much success in the Australian electronics industry, because a small electronics company with a good idea can prototype on an off-the-shelf board, and they get the full software stack, they can, they do the hardware design, and they can get a product out the door quickly. And so I actually lied, that's not my last slide. This is my advice for you. If this stuff interests you, get yourself a cheap FPGA prototyping kit, a vanilla one, not a Zinc one, they're a bit expensive, but Digilent, lots of other companies, right? There's free versions of the design tools. You can play with this stuff. The internet is awash with how to learn VHDL, FPGA 101 type content, right? It's everywhere. So you can teach yourself. Don't wait for us to teach you, okay? I mean, do take 4010 if you're interested, because it's a great course, but you can learn a lot of this stuff yourself. Put on my CSSE 2310 hat, learn Linux. Like, I tell the class this stuff for a reason, right? Because this is what the embedded sector uses in Australia, right? So if you want to be employable, I mean, I know you're robotics folks, and I've offered my apology there in terms of where the focus of this talk's been. But if you haven't, take CSSE 2310. It's not that scary, I promise. Comp 3310 if you want to dive a bit more deeper into the operating system side of things. Get yourself a Raspberry Pi and start playing with it. Pick a project. Pick a home automation project. Pick a robotics project. Right? Do something with it. Right? Any kind of little technical thing. Hassle an academic for a thesis project. Nice and early. Come with some good ideas and a clear kind of motivation and an interest. That's what we're looking for. And if you really like this stuff, I Googled, and one of the cheapest kind of Zinc boards, they're pretty old now, but about 300 US. So I accept that that's a pretty hefty investment for a student. But if you've done FPGAs 101 and you love it, and you've done some embedded Linux and you dig it, this is a pretty natural step. And the things you can do here, I mean, I ported the ArduPilot UAV software to this board about 5-6 years ago, because I was into drones and all of that. You can do so much on a board like this, right? But above all, just stay curious. If stuff interests you, pursue it. You've got, the first time I used the internet, I was in the 3rd year of university. Right? You have the entire knowledge of the world, technical and otherwise, at your fingertips. You can learn anything. Right? We can give you a piece of paper, and maybe we can work more closely with you to help you understand. You can learn anything, right? So stay curious, pursue your technical interests, and yeah, that's all I got. Sorry for the race to the finish. Thanks, folks. We got there in the end. I do have time for a couple of questions, and I've got to bail and try and get a bus.
thank you for coming.
Oh, I got a mug.
A nice mug, yes.
Ah, thanks, Jay. Look
That's
at that.
okay.
Nice, nice. Thank you very much.
Did anyone have any questions in the audience? I had one.
Yeah.
I worked with a fellow who said that the throughput of connections is really important. So like, if you think about like the transmission loss from a 10-meter Ethernet cable is the same like per millimeter for FPGAs. They've got to have like everything's got to be densely packed.
Right.
Is that something that you need to concern yourself with when you're actually programming it? Like how far the gates end up being from each other?
It does it automatically.
Yep.
And when your design is not kind of filling the chip to the sides, you don't have to think too much about that. I mean, there's timing and all that sort of stuff. Once the design starts filling up and the place and route tool starts running out of options of where to put something, then it's sometimes with really complex designs, you actually have to manually get in there and kind of do what they call floor planning, which is like, you know the design better than the tools do. So you kind of, you nudge it, you say, put this bit here, this bit here. So that's a pretty miserable state for a project to be in. You know, when you start the project, you're only filling the chip to 70%, and so that stuff's pretty easy. But then as the design fills, and you start to fill the chip, and place and route that used to take 30 minutes now takes 4 hours and doesn't converge. So yeah, it does come a point in the design phase in the design cycle where you have to kind of pay a little bit of attention to those sort of details. Yeah. All right, thanks guys. I'm so sorry to dash. We had a bit of a late start, and as usual, I talk too much. Thanks very much for the invite. Thanks for the mug. If you're interested, you're welcome to send me an email. I'm relatively available.